I'll try to convey to you during this talk why this mission is timely, is interesting and exciting. And we're going to start by talking a little bit about how people try to look at the origins of life. And basically there's two different ways of doing this. We can look backwards, that means starting from what we know about microorganisms and biology. We also have at our disposal chemistry, which is one of the fundamental sciences that underpins biology and all life. And since a few years, we also have at our disposal the possibility of performing genetic analysis. The other way is to go forward, and that means starting from things like the origin of the terrestrial planets or the evolution of the solar system, and we can use physics and chemistry and fundamental laws that we have seen are valid for most of the universe around us. And somewhere in the middle of that is geology, which is where, let's say, organic chemistry and the mineral world meet, and which has played an important role in facilitating or making possible this evolution from elements to system that gave rise to the first proto-organisms. Now, the ancient planets were very different from what they are today, and in particular Mars, 4 to 4.2 billion years ago, would have looked very different than the cold desert that is today. One thing that is missing in this movie is very vibrant and active hydrothermal activity that would have prevailed in the beginning. Probably would have seen spewing out clouds of ashes that would have been moved around by the wind. In this movie, as we progress forward, we actually move forward in time. So you will see Mars becoming gradually drier and drier. So we see that Mars is an interesting target, and for several reasons. It is relatively close to us, we can land on it. It has a very interesting past. So about 4 billion years ago, conditions on the surface of Mars were similar to those of Earth when life appeared on our planet. So this marks Mars as a prime candidate for exobiology or astrobiology investigations. On top of that, not only is it a planet with an interesting past, it is a small planet that hasn't experienced plate tectonics, where we can find very old rocks in a good state of preservation, material that we can no longer study on Earth. So the mission I'm talking about, the ExoMars 2022 mission, has for scientific objective to search for signs of past and present life on Mars. We are really focusing on extinct life from Mars's distant past. But were we to happen by chance upon active organisms, it would be relatively easy to detect them with the payload we have. And you see that a very important element of this rover that distinguishes it from other rovers is this drill that you see at the front. We're going to talk more about that. But because of this drill, we have this possibility to investigate for the first time the subsurface. The deepest that any mission has been able to drill on Mars to collect samples for analysis is 6 centimeters. And this is not going to change with Perseverance, which has the same type of mini core. So this drill with a 2-meter reach is an important first, and we will discuss why this is there. But it is not only the rover that will conduct science, also the lander has some instruments. And the goal of the lander is to study the surface environment, and by surface environment I mean the climate, the surface and the subsurface. But this lander, of course, doesn't move. So there are 13 instruments in the lander, but I'm not going to talk about those. I will focus on the Rosalind Franklin rover. So to try to understand why we went to all this complication of putting a drill on a rover, let's just discuss first a little bit the surface of Mars. You can think of the surface of Mars as having an ocean, but it's not an ocean of water. It is an ocean of dust, and this dust is a result of millions of years of meteoritic bombardment that have pummeled the surface rock into a fine powder. This and the effect of wind erosion have moved around this material. And this is not very interesting for us. And the reason is that the dust would have been circulated around and sterilized by the high doses of UV light that penetrate the Martian atmosphere. So what we are interested in really here are the icebergs, so to say. And these are these things you see in this image called outcrops. An outcrop is a bit of indigenous rock, so not a rock that has been transported from somewhere else by water or moved by wind. No, it's a rock from that place. And the tip of that formation breaks through the dust, and we can actually see it. We can actually see it from orbit, and we can study its mineralogy, and we can establish whether it's the right type of minerals that we would like to study. And it's on the basis of that that we select our landing site. So the beauty of these outcrops is that it gives us a window, if you like, into the mineralogy of what lies underneath. And that is a real target. And we're going to see why now. The atmosphere of Mars is very, very thin. It only has a pressure of 6 millibars, whereas here on Earth we have a pressure of like a bit more than 1,000. So it is so thin that the UV light from the sun is not attenuated very much by the atmosphere and penetrates and bathes the surface. And any living organism or molecule, organic molecule, that lies exposed on the surface would quickly be destroyed by this UV light. This UV light also produces interesting photochemistry that results in very aggressive oxidant compounds that are mixed in with the soil. How deep they go depends on porosity, on the amount of water, and which model you believe, but let's say in the order of a meter. Now normally these oxidants lay more or less dormant, but when the right level of humidity is reached, they can actually become reactive and degrade or destroy the chemical signatures that we would like to study. And finally, we have ionizing radiation, that it's the radiation, the cosmic radiation from the center of the galaxy that penetrates also the atmosphere and even penetrates into the soil. And there it can also degrade any organic molecules that might be trapped in the geologic record. So you see that we have actually defined sort of a degradation horizon. So what is the ethos of ExoMars? Is to try to, yes, investigate the right mineral we want to see on the surface at the tip of that outcrop, but then map how the outcrop goes into the subsurface and drill and collect samples from below this degradation horizon. In other words, we use all the material above the sample as a shield against ionizing radiation. So on this picture you see the rover on the left. On the right you see how the sample is collected. The sample is like a little piece of chalk. It's like 3 centimeters in length by 1 centimeter in diameter. And it takes us almost 5 days to get down to depths in the order of 1.5 to 2 meters. So we're going to see how we go about investigating things. The most important thing is we need nested observations. What does it mean? We start like we see, so at broad panoramic scales, let's say at hundreds of meters to tens of meters in scale. And we do this with cameras, for example. But then progressively we focus our observations into higher and higher resolutions and smaller scales until we end up with analysis at the molecular scale. So we start with cameras, and here we have a complex instrument where at the extremes you see what are called the wide-angle cameras. They see more or less like the human eye sees. For those of you who like photography, it's like a 50mm objective on a camera. Then there is that large black lens. That's the high-resolution camera. That is like a 300mm objective. And we use that to get higher magnification images from targets that we could potentially approach. Now, on Mars, everything looks brown, so it's very difficult to tell whether A is more interesting than B. So to help us with that determination, we have this Russian infrared spectrometer called ISEM. ISEM is co-registered with a high-resolution camera so that whenever we take a high-resolution image, we can get information on the bulk mineralogy composition of the thing we are taking a picture of. And this helps us to determine whether we should go in this direction or that direction. As we move, we need to learn something about the subsurface because it takes so long to obtain a sample. It is a big investment in terms of mission time whenever you decide, I'm going to drill here. So we have two instruments that tell us about the subsurface. We have a neutron detector that tells us how much water there is in the subsurface. And believe it or not, we don't want a lot of water because that complicates the crushing of the samples. And we have a ground-penetrating radar that gives us the stratigraphy under the rover with a resolution of 2 centimeters. And it has a penetration in the order of 1 to 2 meters. So in this sketch, for example, you see some wind deposits at the top, some sedimentary filling, and the target formation that we would like to drill into in this sample is at 0.5 meter. when we get close to an outcrop, we would like to study it for morphological biosignatures. What are those? We have no hope of being able to spot or see a single microorganism. They're way too small. Their typical size is in the order of a few microns. However, if we happen to chance upon a colonial type of expression, let's say a microbial colony of several hundreds of millions of individuals that could have left an imprint on a rock, that we could have a chance to see. And then we would like to try to understand what shape it has, if there are any biolaminations, the shape of the mineral grains, etc. And for that we have this close-up imager that is at the base of a drill. So we use the drill, we can actually move the drill to point it in different directions. And it has a set of mirrors such that it can look to the front, or when we raise the drill, it can look in two different directions. So the other important bit of kit we have is the drill itself. The drill is like a mini oil platform, and you actually have to assemble 4 elements in order to reach the full 2 meters. And so here on the top right you see the tip of the drill with a sample piston retracted. You see the blades, which are coated with diamonds. And at the bottom you see that light. We have integrated an infrared spectrometer in the drill, which shines infrared light through a sapphire window to the side. So as we drill, we are able to interrogate mineralogical composition in the borehole. The spectrometer actually lies outside. So we have optical fibers that take the infrared light onto the spectrometer. So here you see a little movie showing the rover. You see the antennas of the ground penetrating radar on the back, and here the drill is coming out of its drilling position and preparing to deliver a sample to this little hand that will come out in the front. And the sample is dropped there and then is taken inwards into the analytical laboratory. As the sample is delivered by the drill onto this little hand, we can watch it or take images of with a high-resolution camera and with a close-up imager. And here you see the carbon copy of the model of the flight rover that we have on the ground. We were doing some tests 10 days ago. So here you see the qualification model of a drill delivering a sample onto this little hand, and then an image of the sample taken from above. This was not a drilled sample, it was actually put in the tip of the drill. It was there because we were trying to determine what should be the distance between the drill tip. You see the brushes surrounding the drill tip. They are there to get rid of the dust when we retract the drill during the evening, because the temperature at night on Mars plummets to minus 120 degrees, so we always need to make sure we disassemble the drill at night. This is a view of the analytical laboratory drawer inside. It has 3 instruments, 2 devoted to mineralogy and 1 to organic molecule analysis. You see on the top left, that's the hand and the mechanism. The analytical laboratory is constructed on 2 layers. So I just got rid of the electronics at the top. At the bottom you see something that looks like a carousel. We'll examine that in more detail in a second. But it has a complex set of mechanisms. There is that hand that can move in and out. There is a dispenser of blanks. These are, let's say, material that we know very well, and we know it contains no organic molecules that we can use to calibrate the instruments, but more than calibrate, is to assess the cleanliness of the instruments. And then there is something that functions very much like a coffee grinder in an espresso machine. You have a crusher with a fixed jaw and a movable jaw that crushes the sample into powder, and then it goes into dosing stations, and there is a little revolving sphere that determines how much powder material is paid out. So when the sample is released by the drill, the first thing we do is crush it. So we end up with crush that we deposit on a refillable container. The first instrument to look at it is called micrometer. You know how when you take an image it's red, green and blue? Well, here is red, green and blue plus 320 infrared spectral steps, which means that every pixel in this image is actually an infrared spectrometer column. And we use artificial intelligence inside the rover to classify the crushed mineral grains. We actually examine for every pixel the infrared absorption bands and determine what class of mineral it belongs to. And we use that to compare it with a list of priorities, and then we can move the sample tray under the point and shoot instruments. We have a Raman spectrometer that also gives us mineralogy with a green laser, and for the first time we are extracting organic molecules with a UV laser. Is this laser desorption mass spectrometry analysis, and we do this because the deposition of energy is so fast that it doesn't have any time to dissociate the oxidants that have plagued Curiosity's search for organic molecules. When Curiosity puts Martian samples into the ovens and heats them up, the oxidants dissociate, they liberate oxygen that oxidizes organic molecules, and then you end up with basically CO2. So this is a big challenge. We also have ovens. We have 30 ovens like Curiosity or Viking, but we have tried to tweak the way we use them so that we don't suffer so much from this dissociation of oxidants. So the sample typically for this first analysis goes into what we call the refillable container, which is this little bathtub, which we can use, fill it up. When we're done with the analysis, we clean it, so we can use it effectively infinite times. Whereas the ovens are once, or we are investigating perhaps twice use only. So that is what we call a consumable. We have a finite number of ovens. 20 of these ovens, we just use heat. On 12 of the other ovens, we actually have special compounds for doing what is called wet chemistry. These special compounds can attach to certain molecules to protect them so we can do a better analysis. The main instrument for doing the organic molecule analysis is called MOMA, and at its heart is this ion trap mass spectrometer you see here. So here in this movie you see how we drop sample powder in the refillable container, and now we're going to turn on the UV laser. The UV laser fires trains of pulses of high power UV light that strike the sample and release the organic molecules, which there is a very fast acting gate that allows them into the ion trap mass spectrometer. In the ion mass spectrometer, we can go through a process of separation and enrichment that allows us to concentrate on certain targets and actually re-ionize them to do two-dimensional mass spectrometry, which is a very powerful technique. The other way we have to look for organic molecules is by using the ovens. In this case, we close them with a zirconium sphere, and we can heat them to very high temperatures if we want to. And then we have gas chromatography columns. We have 4. This one you're seeing here, you see the soup of organic molecules, and the packing material in this column actually separates them by molecular weight. So the light molecules come out first, and the heavy ones come out later. Here they get ionized, and then the fragments get analyzed in the mass spectrometer, and that is the way we can determine what the mother molecule was. This instrument and the others are described in this volume that you can see. It's free access. But to give you an idea, this MoMA that does the organic molecule analysis by itself is bigger than all the rest of a payload put together. And it's one of the most expensive instruments, at least I have worked with. It's somewhere around 120 million euros, and thus and in the size of a shoebox, does what it takes roughly the size of 3 washing machines to do in the university. So a lot of this effort has gone into making a very powerful instrument very, very small. As you can imagine, we need to be super sure that the parts of the mission that will come into contact with the sample are ultra clean. So clean that they cannot be assembled in any laboratory where human beings can go in. So the people you see here working in the Analytical Laboratory drawer, they are working on the parts that are peripheral. The actual ultra clean zone part was assembled on that glove box train you see in the background that says ISO 3. And the level of cleanliness there is equivalent to that used in facilities where people work with Ebola virus or very, very, very dangerous and toxic molecules. It takes about 2 weeks for something to go into that thing and proceed through the 4 stages until the assembly stage. So here is the last picture we took of the Analytical Laboratory drawer, ultra clean zone, and this was taken from the outside into that glove box train. Every single nut, bolt, screw, bit of glue, whatever that was used in there had to be heat treated, sterilized, had to be labeled and put in its container there, and people assembled everything working from the outside using those gloves. Here you see the integration of the fully assembled and pressurized Analytical Laboratory drawer into the rover bathtub. This was done in the UK, where the rover was put together. The Analytical Laboratory drawer takes about 2/3 of the volume in the rover body. The rest is taken by the service module, which has the transmitters, the battery, the computers, the inertial measurement units, etc. So the service module is the part that has the silver cables and the golden stuff towards the front, to where the people are pointing. That's the Analytical Laboratory drawer. Here you see The drill. This is an accelerated movie because in reality it moves very, very slowly. The close-up imager is not yet attached in these images. And here were the first tests we were conducting with a rover. Notice that it has no wheels yet. This was at Airbus in the UK, and we were integrating the mast. Here the rover has been raised to turn on the ground penetrating radar. It was elevated about 3 meters over some metal targets to carry out that calibration. And this was taken about three weeks ago when it went to Cannes for tests. So this is a flight model of a rover. You see the lander on the left, and it was coming in. There's the rear jacket of the capsule on the back left, and you see the rover. You see the wheels look strange. We're going to talk a bit more about that in a second. And the rover has many, many cables. The white ones are actually for thermocouples, like thermometers to measure temperature. Those don't fly, but the silver ones do. Here's another view, this time taken from the back. You see the antennas for the ground penetrating radar, those orange things, and you see the camera, the white rectangle with the red filters in the front. It's folded backwards because the mast has been folded back on top of the solar panels. The rover actually doesn't attach directly to the lander. It attaches to a plate in carbon fiber, and then this plate is actually screwed onto the lander. And it's through this plate that the rover receives energy after landing. So here you see the flight model of a rover hooked onto the lander. You see some of the lander's solar panels, and on the top right you see that funny looking thing. That's the antenna that the lander uses to communicate with orbiting satellites, because actually neither the rover nor the lander can talk directly to Earth. You would need an antenna way too big for that. So typically what you do is you have 2 communications windows with flying satellites that pass overhead. So in the morning we tell the rover what to do, and in the evening it tells us what it did. Now, one thing that is cool about this rover is the locomotion system. The locomotion system has all 6 wheels are driven, but crucially all 6 wheels can steer. The US rovers actually steer only the end wheels, not the wheels in the middle. This provides us with some other nice possibilities to move. For example, we can crab. What does this mean? It means you can move all 6 wheels in one direction, and then you move the entire platform sideways. This is very useful. For example, imagine you have a formation in front of you, some rocks you are interested in imaging, and you don't need to go back and forth a million times to maneuver to actually be able to cover with images that rock. You can actually turn all wheels 90 degrees and actually crab sideways while you image. Another thing that we have in this rover that is interesting, on the sketch on the right, you see above the wheels, those cones, those are the steering motors. And then in blue, a little bit inwards, you see these blue cylinders. Those are other sets of motors that we call the knees. And these knees allow the rover to use the wheels also as feet, which is sort of an emergency motion possibility that we have. So you can think of a rover as sort of a supermarket trolley. It works great in a parking lot, but when you take it to the beach, you run into trouble. So let's assume that we are happily rolling along and we hit a patch of very sandy or loose soil and the rover gets stuck. At that point, it would stop, call home and say, I have detected excessive slippage of my wheels, I'm stuck, what do I do? And then we can command the rover to go into wheel walking motion, which I'm going to show you in another slide. The other thing that this rover has that it's pretty unique is that the wheels are flexible. We have a complex set of steel and titanium springs that allow the bottom of the wheel to deform, which is the same thing you do when, let's say, you go to Australia and you want to cross a dry riverbed with your pickup truck. What do? You take air out of the wheels. Well, we do the same thing here. Even though the wheels are 28 centimeters in diameter, they have the footprint of a 40 centimeter wheel because they can flex at the bottom, increasing the size of the contact patch. So here you're going to see the facility that we test. We can incline this whole thing, fill it with whatever we want, and we use that for making locomotion tests. So here you see the rover going up a pretty steep hill of 21 degree slope, and you see it's moving on a material that has a consistency of flour. So normally you get stuck in no time in this type of terrain. But when we invoke this wheel walking motion, not only can we get out of it, we can actually even climb dunes and very steep terrains with it. So this is a little bit, we're coming towards the end part of the talk. I want to tell you a bit about the mission. So the launch window opens on the 20th of September and closes on the 1st of October 2022. And the landing will be on the 10th of June 2023 at 15:32 UTC. So it doesn't matter at what moment in that launch window we launch, we always land at the same time. Now here are some pictures of elements of the mission. On the left you see the carrier module. The carrier module attaches to the base of the, well, not the base, the bottom of the capsule as you see it on the right image, and is the bit that has solar panels and a propulsion system that can make correction maneuvers on our way to Mars. Attached to that is a capsule that will actually take us to the surface. In this picture, which was taken in Moscow, something I forgot to mention is that this mission and the entire ExoMars program is a cooperation between ESA and Roscosmos, the Russian Federal Agency, and it has some contributions from NASA as well. Here you see a picture during the assembly. Actually, this is a structural model of the lander, and you can see the ramps through which the rover will descend, and you can see elements of the wheels and one of the solar panels. In this image instead, this was taken in Torino in Italy, where the main assembly center is and where the rover operations control center will be. You see the lander, and you see there's a lot of cables in this lander. We're going to see it get progressively more and more complicated. On the left you see the rear jacket and the lander, and on the right everything has been turned upside down and put into the capsule. What you have just watched is a drop of a test article to make sure that the wheels will be able to take the landing shocks. And we're going to see a few of these tests. This one was done in Moscow, this one as well. explosions that you hear are the pyrotechnic devices that actually fire the logs. So this picture was taken about 2 weeks ago. Here you see the lander, this time with a rover inside, and the rear jacket that is being lowered onto it. And we had to make, let's say, special tests to determine the position of the center of gravity and the moments of inertia, and then decide where we were going to place the balancing masses to make sure the spacecraft could rotate during cruise. And this is the actual flight composite as it will go to Mars. So you see the carrier module on the base and the actual flight capsule at the top. And I would like to finish with this image, which I like a lot. It's from the integration team in Torino, right before the spacecraft composite was shipped to France in Cannes for the last tests. As of last week, the entire spacecraft assembly is back in Torino, where we are beginning to do other tests. We have to do a few repairs on the rover and some other important verifications. And now we move on to more into the software testing stage. And with this, I'd like to thank you all so very much for your attention. And remember, 10 June 2023, it should be a good adventure. And hopefully we will have, in not too long after that, important discoveries to share with all of you. Thank you.